Dr. Greenborg, you have a message from Mars. Please report to administration.
Control applications of Toro, a torque-controlled humanoid robot. The self-contained robot Toro was developed as a research platform for walking and whole-body control. It has a total of 39 degrees of freedom and can be operated both in position and torque control modes. Here, the highly sensitive inner loop joint torque control is demonstrated with an impedance controller for the whole body. The walking controller is based on the divergent component of motion, also known as capture point. The high-level walking commands for the robot can be autonomously generated or it can be introduced via proportional velocity input using the remote control of a gaming console. Footstep locations define reference trajectories for the DCM, which correspond to ZMP trajectories on the robot feet. These trajectories are tracked with a feedback control. Note that Toro pulls the safety crane, which acts as a disturbance for the controller. While walking, the upper body works in impedance mode. The maximum speed that the robot can attain is about 0.5 meters per second. The feet are relatively small with a length of 19 centimeters and width of 9.5 centimeters, which represents a bigger challenge for keeping the overall stability of the system. Based on torque control, different impedance behaviors can be easily realized, as demonstrated here with an energy-based limit cycle controller used in a simple handshaking demonstration. The desired energy level can be manually set to 0, which dissipates the arm oscillation, but the arm will swing up if the energy level is restored. A multi-contact whole-body controller for balancing and posture stabilization is implemented using optimization of contact wrenches, while taking into account frictional restrictions and center of pressure limits. Here, the controller is demonstrated in an application where the robot is balancing on a rocker board. The changes in the slope of the board recreate uncertainties of the supporting terrain. Using the embedded IMU is crucial for tracking the posture of the robot, which allows the controller to maintain the balance even on rough terrain. The controller is also able to cope with a changing number of contacts with the environment. The robot uses the active contacts to maintain the COM position and torso orientation, while the unused end effectors maintain their pose relative to a world frame. Ongoing research is focused on further development of the control strategies, for instance for walking on rough terrain. Also, the integration of egocentric and sensory-based planning and control will lead Toro towards more autonomous behaviors.